we got to essentially, so this is kind of all recapitulation. We looked at the satisfaction relation here. Again, we looked at that a second time. And this then gives us a kind of a three-place relation. It's a relation between a structure, a formula in the language, and an assignment function or valuation. So the idea is that this relation is going to say the formula phi, when you assign its free variables according to W, comes out true in M. And the various clauses just reflect the logic of the situation. An assignment is going to make an equation true if and only if, well, whatever it does, it's going to assigns to the term S, it better be the same as to the term T. And then the others are according to just natural logic about what it means for this assignment to make a relation true or negation or an implication. And the bite, as it were, in the definition comes in the last clause. So an evaluation makes a for all universal formula here come out true, means that whatever I substitute for VK, and we look and see what W does for the other variables, phi comes out true. And that's what this says here. It says, whatever A we pick, if now my valuation substitutes in A for what WK did and leaves all the other things the same, then the formula comes out true. So we're assuming, right, when we define this, again, it's an inductive process. I'm assuming we're going to define this, assuming we know this. Right? And this phi is of lower complexity than for all VK phi. So we build up in this way our notion of the satisfaction here. So let's just see some examples of that in action then. Here's the natural number structure. Again, I've got in it interpretation of the plus symbol of the appropriate language is, well, just addition. Right? The ordinary addition, likewise times and 0, and prime is for successor. Right? So something primed is that thing plus 1. Okay, here is a evaluation, right? It's assigned 0 to 23 and 1 to 106. It does other things to 2, 3, 4, but we don't bother specifying that now. So let phi be the formula, which is actually the plus function assigned to V0 and V1. And now, I'm just getting some paper. Of course, when I write, I mean, a function is usually written something like this, right? F of V0, V1. Right? But it's kind of silly when it's plus because we're so used to putting the function symbol between the two things that I don't even bother writing it like that. Although formally, if you were programming it, you would have to write it something like this. But of course, we put the plus in between. So this is saying V0 plus V1 is 0 prime prime. So this is syntactic. This is just a string of symbols. Okay, on the other hand, with the W we've got, it's not the case that this assignment W makes this formula come out true, for the obvious reasons that W is going to assign to 0 prime prime, right, or W star, right? It'll assign 0 to, sorry, the 0 symbol to the actual number 0, and then it'll assign the prime thing to the double successor of 0, in other words, 2. So here I'm thinking there's 2, it's a number in the natural number structure. Okay, and then W is then going to, or W star officially is going to assign to V0 23 and to V1 106. Right? So W star applied to this function, applied to these two variables, is the interpretation of the function plus, and then applied to the interpretation or assignment of V0, which is 23, and then to V1, which is 106. And I apply the function, the adding function, in the natural number structure, and I get something that's not 2. Right? So this assignment makes this formula false in N. Okay, more interestingly is something which has got a universal quantifier in front. So phi says for all V0, V0 plus V1 is V1 plus V0. So we know what this is going to be interpreted as. It's like the commutative law for addition. But again, this is just a string of symbols. On the other hand, any assignment is going to make this string come out true in the natural numbers. And intuitively we know that, but we just see how the mechanics of this works. What is the definition of an assignment to a universal formula? Well, we go back to this line of the definition here, and it says, okay, whatever I substitute for VK, better make it come out true. And that's all that's written down here. I pick any object in N, right? I look and see what happens. My quantified symbol is for all V0, so whatever I substitute in for V0, for any K that I pick here for V0, I haven't bothered to specify what W does to 1, because whatever it is, it's going to make this true. Here. Probably there's a bracket that should be there, right here. And I don't know what this is doing here. Let's get rid of that. Here. So here I'm just, doggedly working out the clauses here, right? This will make this equation true in N if whatever it does assigns to this side of the equation or to that side of the equation, they're the same. And that's what I'm looking at here. I'm checking that the evaluation here, what it does to the left-hand side of the equation is exactly the same as what I do to the right-hand side of the equation, right? So this is going to say K plus, well, whatever W1 assigned is the same as, well, that W1 plus K, whatever the K is. And this is true if and only if for all K, K plus, well, V1 was 106, assigned 106, and K plus 106 indeed equals 106 plus K. Again, any questions about this? This is, I hope it's just straightforward. I think this one here is, now it's doubly quantified. The only difference is it's got a for all V1 as well. So actually there are no free variables left in here. All the variables in the formula have been bound by the quantifiers. Right? So now one would, go through it in the same way as before. We take some W, we'd look at this phi here. This makes this true if for all K, doesn't matter what we apply to V1, whichever K we substitute for V1, the other things that W assigns will make the rest of the formula true, which is what's written here. But of course, I still got another for all quantifier to deal with here. So that's going to mean for all L's that I substitute for V0, the formula comes out true. And here I've written this. This is an L down here. And this is an L. And this is an L. So then the rest of the maneuvers are the same as before. So notice that actually the valuation, in a sense, plays almost no role in this. Right? There were no free variables in this formula to worry about. The only reason this W is carried along is so that I can start writing things like W of K for 1 and L for 0. All that mattered was what happened to V0, the instances of V0 and V1. Right? So the other values, the W is entirely irrelevant in this. So we indicate that situation by just dropping it. Right? If the free variables of a formula, if there are no free variables, then phi is called a sentence. And we just write this. Phi is true in M. And we drop the W's because it just says, you know, for all or any W in evaluation, W will make phi come out true. The question is W0 just the same as W star of V0? Yes. The W without the star is just the function from n into the, it just gives us an n sequence of natural numbers. And W star of V0 is whatever W of 0 is. Here we go back down here. So W star of V0 is W of 0. So a bit more notation. Instead of just one sentence, if I've got a set of sentences, often written as a gamma, capital gamma or delta, something like that, this is just shorthand for saying all of the sentences in gamma are true in M. And now there are just some obvious facts about the definition. W makes not phi true in M is, well, just according to this here, it just means that W does not make phi true in M. Okay? And not, here we just write a stroke here through this double turnstile. So W does not make phi true in M. And we're using just two-valued logic. So something is either true or false. So if this doesn't happen, it means that not phi is true in M. I can't have something both being satisfied and being not satisfied at the same time. Right? So I can't have that and that occurring at the same time. If W makes phi come out true in M, and W makes this implication come out true in M, then W makes the consequent here come out true in M. There's nothing deep about that. It's just what we mean by arrows and again, the basic definition of the satisfaction relation. As I said in the recorded lecture, I'm taking, arrows and not and for all as basic, right? And I think Charles took not and or and exists as basic. It's no difference. Makes no difference other than just what we write down in the definitions. So I can define and or in terms of not and arrow here. This is by implication. That just says phi arrows psi and psi arrows phi. Well, W is going to make a by implication true if and only if it makes both of them true or both of them false. And that's one way of putting it down here. It makes, here's W, it might make phi true in M, in which case it makes psi true in M. Or maybe it makes phi false in M, not true in M, in which case it'll make W. W will make psi false in M. And if you look at what the definition imports about the existential quantifier, again, it exists Vk. This is just the same thing as it's not the case that for all Vk not something, right, here. Well, if you just puzzle that through, it works perfectly. W makes exists a Vk phi come out true. It means there is some A in M such that I substitute in A in my evaluation for Vk, then the rest of the values of the variables will make phi true in M. So this exists is kind of comes outside, and we just say this exists is true, this existential formula is true, means there exists some A and M, which will make it true. Okay, and that's just a rewriting of this definition here using these abbreviations. Right, can I show the previous sheet for a moment? So this is the kind of trouble with this format is I'm not sure exactly what, I don't see the chat until a few minutes after it's relevant. Somebody was asking this previous sheet. I don't know what you want to read off this previous sheet. Okay. Can you have a formula that is not a sentence, but is true for all valuations? Yes, we'll be coming to those. They're called universally valid, and they are will be of great importance to us. But not yet. Okay. If there are no more questions about that, I go on to the next subsection, which is about substitutions. Right, so I'm looking at, I hope the numbering is 3.3.3, page, I hope 51, substitutions. Okay, so what's the idea here, right? I mean, if I've got a formula, phi, say, and maybe variable Vk is one of its free variables. Okay. I might illustrate that by just writing down phi with Vk here. So we think of the formula as saying something about, well, whatever we assign to Vk. So if for phi I've got down here, it's not the case that for all V1 equals V0. Suppose phi is this here. What's the intention? The intention is it's not the case that everything that I substitute for V1 equals V0. So saying there is something besides V0. So this is going to be true in a structure as long as the structure's got at least two elements. Okay. So this will be true in any structure, right? For any assignment. As long as there are two elements. in the domain of the structure. Now, what I can't do is come along with this formula and substitute in any old variable for V0. It wouldn't matter if I substituted in V1 equals V3. The formula will have the same intended interpretation in the structure. But if I then substitute in V1 for V0, I've messed it up, right? Because this just says it's not the case that everything equals itself, which is going to be false in any structure. So it's not safe in general to substitute things in for free variables in a structure, to change the free variables. You can do it sometimes, and you can't do it in other times. We saw an example here. I could change V0 to V3, but not to V1. One can have more complicated issues, right? I might have this formula here, V1 equals V0, and I'm going to substitute in here a term V, and maybe this term here is V3, V4. So here's phi. So I look at phi and I substitute in f of V3, V4 right here for V0. And this would look like this. And all is fine. But you can see what is dangerous here. What if V3 actually was V1? Okay. Now, after I do this substitution, I've got this. And I could now have changed the meaning or my intention, because now this V1 is connected to this V1 because it's quantified here. Here there were still two free variables in this formula. But this says something about tying down this first variable to being this. Right? So the intended meaning is very likely changed if you do something like this. So it's always a rather fiddly okay, so it's always a rather fiddly part of the course, this kind of substitution in of terms for variables. And there's no kind of nice slick way around it. I wish there was, but one just has to have this kind of rather kind of fiddly definition of, you know, when you can substitute in a term for a variable, right, in a formula. And it confuses people. I mean, you have to look at it and try and work out what's going on. But there's no avoiding it, right? So all I would recommend is you look hard at how this definition 338 is going to operate, right? And just try and absorb the cases that arise. So we'll look at these now. So this is definition 338, or it's also 3.8, right? This is just in the recapitulation, right here. So T is substitutable for VK in a formula phi. So this is going to outline for us when it's safe to do a substitution and not mess things up. Well, I can always substitute in if phi is atomic, right? Remember, atomic formulae are either equations or just relation assertions, or phi is not psi, and I already know that t is substitutable for vk and psi. So you can kind of see the inductive nature of it. I assume I know the property for this psi, and then I have it for this more complicated formula. Or what is phi? Phi is an implication, and I know that t is substitutable for vk and psi and chi. And then the all-important clause, the last one, is just as here, we've got a universal quantifier that may mess things up. It's for all vk psi, where t is substitutable for vk and psi. And then the all-important $64,000 part of this definition here is this last thing, which stops mistakes happening. So it's an implication. Sorry, let me stick with the Vn. Here it's Vn in the notes. There's no reason why it should be the same K as here. So phi is for all Vn psi. I know I can substitute T for Vk in psi. So it had better be if Vn is one of the free variables of the term, which is exactly what happened up here. V1 was one of the free variables of the term that I might put in. So if this happens, then actually K is such that Vk is not a free variable of phi. So it's sort of saying, if I try and do something that's dangerous and goes wrong, I'm trying to substitute in for a free variable, but actually I'm okay because that variable was not free in phi. So again, it's a definition by recursion, right? So we assume we know what being substitutable for Vk is in a simpler formula and deduce what it is to be in a more complicated formula here. So there are a number of properties to get from this, right? So if t is not substitutable for a variable Vk and some formula chi, then if the formula chi is longer, make it longer, it's part of something else, it won't be substitutable Vk in that longer formula. So I say a longer formula. Chi is a subformula of psi. Then Vk is not substitutable. Sorry, T is not substitutable for Vk in chi, in psi. Right, so if a term is not substitutable for a variable in a part of a formula, it's not substitutable for that variable in the whole formula. I can't make it substitutable by making the formula longer. Now the definition here is, it's also slightly well, there are some, I mean, we didn't say here in the definition that vk was one of the free variables of phi. We didn't actually specify that here. Right? So we allow in this definition to say that t is substitutable for v3000 in phi, even if v3000 isn't one of the variables of phi, either free or quantified. So it's kind of a default thing. So we allow substitutability for variables that don't appear here. So we're allowed to say that t is substitutable for vk in phi, even if vk does not appear in phi. Right? Of course, in general, we're thinking of the substitutions for when this vk is a free variable. So the definition is specifying some kind of defaults as well. Right? Well, I'm pointing out some of the defaults that are there. So I've said here on the notes, it leads to some peculiarities, right? When vk is not free. Right? If the variable is not free, right, it does not mean that a term is substitutable for it. Right? There are some examples we'll see in a moment. But when vk is free, the definition functions perfectly fine. Right. We'll look at some examples. Back on example 310. I mean, Charles had already put an example out for us. Okay, so stop me if you want to ask anything. Okay, so let's look at these examples. Yeah, let's go through them. So we've got R is binary, F is binary, G is a one-place function, H is a ternary function, three-place, and A is a constant symbol. Right, so V0 is substitutable for itself. If you look at the definition, it's substitutable for another variable, right? But it's also substitutable, and this is what I was saying, officially it's substitutable for a variable that actually doesn't appear. We're just talking about potential here for substitution. And the same is true here. Difference is that we've now got, I've just put this function in instead of V0, I've substituted in this function, but V0 is substitutable for V0, V1, or V2 here. V0 and V2 are both substitutable for V0 in, well, let's just change, it's exactly the same if we write for all as exists here. V0 and V2 are both substitutable for V0 here. If I substitute V0 for V0, of course, this just stays the same. And substituting V2 will just change that V0 to a V2. It won't change the overall intended meaning of this formula. But as we saw before, if I substitute in something that's then bound by the quantifier, I change the meaning. So V1 is not substitutable for V0. Okay? But the clause does actually allow us to say V1 is substitutable for V1, rather trivially. Okay?
Sorry,
Yes?
for part I, how is V0 substitutable for V1? Because if I substitute V1 for V0, then surely I would get RV0 V0, and doesn't that change the meaning?
But I think you said it the other way around. I'm saying T is substitutable for V1, meaning, oh, I'm sorry. No, I beg your pardon. I mean, I'm wrong. It is substitutable. It's not bound by a quantifier. Let me just check that I've got this. This isn't, T is, it's one of the free variables of, yeah, I mean, it's, yeah, I mean, you're right. It does seem to make it look like, you're changing the meaning slightly, but it's saying about all possible objects, I guess. No, I mean, we stick with the definition, but you are making a point there. I mean, a reasonable point.
Okay.
Okay, all right. Let's see, where did we get to? Okay, V is not substitutable in here for V0, right? Because this V0 that's free would then become bound. If we change it to V1, it becomes bound to this. We'd be changing this into a sentence. And likewise, I can't plug in not just V, I can't plug in something like G of V1 either, right? In which V1 is a free variable. So if I try to put in G of V1 in here, the V1 would get bound by this quantifier. Okay, I can substitute this term in for V0 here because there's no quantifier. So what I've got is just that V1, well, it's trivially one of the free variables of V1. V1 is a free variable of the term T, if that's G of V1 here, right? And G0 is then one of the free variables of this formula here, right? And that would contradict this part of the clause here, right? If I'm substituting something in for VK, right? If the quantifier outside is Vn, it better be that Vk is not one of the free variables, right? And that's what fails here. I've got V1 is one of the free variables, right? But at the same time, right, V0 is one of the free variables of this formula here. There's 0 missing, misprint there. So V1 is, right, so G of V1 would not be substitutable in here because it falls foul of this clause here at the end. Okay, since V1 is not substitutable for V0 in here, it won't be in the longer formula. That's what I just said as a bullet point above. Nor will it be in this longer formula here, or this longer formula. Okay, constant is always substitutable for any variable, right? Because it itself has no free variables, and it's not going to get clash by being bound by a quantifier. And let's see here, what's here? Here's this three-place function, free variables V0, V1. Okay, it's by default substitutable for V1, right, which nothing happens. It's substitutable in for V2 because V2 doesn't occur here, again, just by default. But it's not substitutable for V0 here, right? Because the V1 that occurs in H will get caught by this quantifier here, right? Because this is me just saying that. V0 is one of the free variables here, and V0 is one of the free variables of this formula here. So again, this clause here at the bottom comes into play, right? Nevertheless, it is substitutable for V1 in this formula because I could, with impunity, put it in there. And now this is a V3, so it's not going to clash with any of the free variables of H that's there. Somebody asks if they're right in saying that the size of the set of free variables should not change. No, that's not strictly speaking true. I could take a formula. I might have a formula here with just one free variable, and I might substitute in a constant for that free variable, right? And now this is no longer got any free variables because the C constant didn't have a free variable. So you can decrease the size of the free variables in that set of free variables that's there. So lastly, before I finish up, okay, so this function f v1 is not substitutable for v1 in here, right? You might think, oh, it is because the default would come into play because v1 is quantified, right? Okay. So even though v1 is not one of the free variables here, right? Recall that to be substitutable for a variable, right, in a quantified formula means it does have to be substitutable for the inner formula, the subformulae, right? And that's what happens here. It's not substitutable for v1 in here because then it will get caught by this for all v0. So you might think at first glance it is substitutable by default for v1 because of this quantifier. But if you look further into it, it would have to be substitutable for v0 for v1 in here, right? But then there'd be another clash, an internal clash. So the moral of all this is we only want to substitute terms for free variables which are substitutable according to the definitions that are there. Right? So I want if a term is substitutable for a variable in a formula, and that is truly one of the free variables of the formula, so we're not talking about the dummy default situation, then doing the substitution does the right thing. Right? Okay. So we'll look at a recursive definition of next time of what substitution actually does, right? So again, just thinking in like programming terms of how would you write down an algorithm to say, I'm going to substitute, you know, X for Y and Z. And then what happens next? Okay, so that'll be tomorrow morning. Are there any questions to be had at this stage? Okay, if not, I'll see you then. Fine.